one day you took your lunch, said goodbye to your family, got into your spaceship, and went off to spend the day exploring. And suppose the first planet you saw was the Earth. If you saw it from very far away, it would look small and round, like a coin. But when you got closer, you'd probably notice that the Earth isn't round and flat, like a coin, but round like a huge ball. You'd never be able to see all of its surface at one time, and part of what you could see would be hidden by clouds. But suppose you could see the Earth without the clouds. You could learn quite a few things about it just by looking. For instance, you could tell from space that large parts of the Earth are blue. Those parts are water. The other parts, which are other colors, are land. The more you looked from your spaceship, the more interesting things about the Earth you'd probably see. In fact, you might try to think of some way to show your parents and friends what you saw. Something you could use to let them know what the Earth was really like. For instance, you might draw them a picture. Or take a picture with a camera. That would give them some idea of what the Earth looked like. But a picture would only show the Earth from one side. So maybe you could take a lot of pictures from all sides. But they'd still be flat. Flat pictures wouldn't really show someone how the round Earth looked. So what would? Well, suppose you thought about what the Earth looked like when you first saw it from far away, when it looked much smaller. A small Earth? This might give you an idea. Why not make a small model of the Earth? What's a model? Well, a model of, say, your spaceship might be like this. It would have the same shape as the real spaceship, and all the parts you could see would be in the same places as on the real one. Your model would just be smaller. You might make your model of the Earth about this big. You could make it round like the Earth, but without clouds, so you could see all of its surface. Now you would have something that you could use to show the people back home what the Earth looks like in a way that would be easy for anyone to understand. You'd have a globe. To make your globe as helpful as possible, you'd probably color bodies of water on it blue and choose a different color for the land so people could easily tell them apart. You'd end up using a lot more blue because on the Earth there's much more water than there is land. And then, to show where there are mountains on the Earth's surface, you could even make some parts of the land bumpy, or make them look bumpy. If you did these things, when you showed your globe to the people back home, it would give them a good idea of what the Earth was like. People would probably be very interested, but they might have questions. For instance, they might want to know whether the different parts of the Earth have names, or if there are countries on the Earth. To answer these questions, you'd need to add some things to your globe that someone wouldn't be able to see from space. You could make another trip, and this time land on the Earth. You'd find out from Earth people that they call their big areas of water oceans. The oceans have separate names, even though they're actually all one big body of water. Here's how they look on your globe. This one is the Atlantic Ocean. Here's the Pacific Ocean. And this is the Indian Ocean. And you could find out the names of the large areas of land. Earth people call them continents. These three are almost like one big continent. They're Africa, Europe, and Asia. These two are also connected, North America and South America. The others are Australia and Antarctica. You could even find out where the boundary lines are for all the countries on the continents. You could see that some of the continents have a lot of countries. Some have just a few. And one continent has only one country. If your globe showed the names of the countries, and the names of the continents, and the names of the oceans, you'd have a globe that would tell people a lot more about the Earth than anyone could see from space, and would also be just like some of the globes that Earth people themselves use to study their planet. But what can people find out by looking at a globe besides the shapes of things and their names? Plenty. Let's take the countries and names away again and look at some other things. When people use a globe, it's just as if they could take the Earth in their hands and turn it to learn about any part they want to see. For instance, if they turn the globe this way, they see almost all land. Turn it halfway around, and they see almost all ocean. Or they might want to look at a different part of the globe, maybe by turning it this way. Right in the middle is a place called the North Pole. Where the North Pole is, there's only ice and water. If they look at the opposite side of the globe, they're looking at the South Pole. That's here on the continent Antarctica. When you see the globe this way, the North Pole is here, and the South Pole is here. There is a line drawn all the way around most globes, halfway between these two poles. This line is called the equator. The equator isn't really drawn on the Earth, of course. It's an imaginary line that divides the Earth into two halves. The Earth is like a ball in space. Another name for a ball is a sphere, and half a sphere is called a hemisphere. This half of the Earth, the half with the North Pole in it, is called the Northern Hemisphere. You can tell somebody where something is by saying it's in the Northern Hemisphere, or in the Southern Hemisphere. That's this half with the South Pole in it. You could also think of the Earth as divided in half through the poles, this way, into two different hemispheres. This half is the Eastern Hemisphere. It includes most of the land on Earth. You can say that Europe, Asia, Africa, and Australia are in the Eastern Hemisphere. And you can say that these two continents, North America and South America, are in the Western Hemisphere. People also use globes to help them think about traveling from one place to another on Earth. Suppose they want to travel from, say, here to here. They can tell by looking whether they need to go over water, perhaps on a ship, or in a plane, or whether for other trips they might be able to go entirely on land, for instance, in a car. They can get a good idea of what they might pass along the way, or what stops they might want to make. A globe can also help people find the shortest possible route between two places on the Earth. Sometimes that's easy to guess, and sometimes it turns out to be surprising. For instance, if you wanted to go from here to here, the shortest route would not be this long line. Instead, it would be this much shorter line that passes near the North Pole. You can find the shortest route between any two places on a globe by stretching a string between them. So, as you can see, a globe can give you many different kinds of information. It can show you where there are oceans and continents, and what countries are on each continent. And the globe can tell you which hemisphere these places are in, and even help you find a good route between places. In fact, a globe tells you so much about the Earth, you might
globes are made to represent the world. A globe is a special kind of map. It shows the world as we think it might look to someone far out in space. A globe shows us the land and water portions of the earth. It shows us the oceans and the continents and their general shape. But how do we know that the actual shape of the earth may be shown by a globe? How do we know what the earth's shape really is? Let's see. Many thousands of years ago, early man looked at his world. He thought perhaps that it ended at the horizon. He may have asked himself, is the world flat, and does the horizon mark the falling off place? Years later, people living near the sea noticed an interesting fact. They saw that ships heading out to sea in any direction seemed to sink and disappear below the horizon. They knew that the ships didn't really sink, so they explained what they saw in this way. On a flat earth, a boat leaving the shore would simply disappear in the distance. However, if the earth were curved, a boat would seem to sink lower and lower as it sailed away. So they thought that the earth must be curved. Ancient Greek scientists thought that the earth was round because of what they sometimes saw when they looked at the moon. At certain times, the full moon became dark, as though a giant shadow were passing over it. What happened is shown in this diagram. The earth blocked off the sun's light and formed a shadow. The Greeks knew that the moon traveled around the earth. When it entered the earth's shadow, it seemed to disappear. The Greeks called this an eclipse. These motion pictures of an eclipse were photographed through a telescope on Mount Wilson in California. We can see the edge of the Earth's shadow on the moon. The movement is speeded up because this eclipse takes almost 2 hours. It was this same curved shadow crossing the moon which the ancient Greeks saw. From the shape of the shadow, they were able to tell the general shape of the earth. They decided that since the earth's shadow is round, the earth itself must be round. Columbus, along with many other men, knew about the idea of a round earth. If the world were round, Columbus believed, it should be possible to sail around it. He failed in his attempt because America was in the way. A few years later, however, a sea captain named Magellan set sail from the country of Spain. His ship sailed westward. Finally, after many adventures, one ship arrived back at its starting point. This voyage proved that the world is round. But then, about 300 years ago, Isaac Newton, a great English scientist, said that the earth could not be perfectly round. This model, made of steel bands, shows why he believed this. When the model turns slowly, it has a round shape. But when it turns quickly, it bulges out in the middle and flattens on the top and bottom. Newton said that since the earth spins rapidly, its sides must bulge out and its poles must be flattened. Later, it was proved that Newton was right. The distance through the Earth from pole to pole is 27 miles less than its distance through the middle. This means that the Earth is slightly fatter from side to side than from top to bottom. The shape of the Earth is like a slightly flattened ball. In this drawing, the flattening and bulging is shown much greater than it really is, so we can see it clearly. But today, satellites traveling around the Earth have given us better ways to measure the Earth's shape. Special receivers on the ground pick up radio signals sent by satellites. You are listening to a recording of the signals received from Vanguard 1, one of the early satellites. From information received from a satellite, scientists can tell its position. They can also tell the path it follows around the Earth. Because the Earth bulges slightly in the middle, scientists knew that a satellite's orbit would slowly change, like this. However, after observing and measuring actual satellite orbits, they found other changes they hadn't expected. Very careful studies of satellite movements proved that the Earth not only bulges in the middle and is flattened at the poles, but that the Earth also dips in a few feet around the northern hemisphere and bows out a few feet in the southern hemisphere. Remember, the differences here and here are very, very small. Only a few feet in many thousands of miles. In this drawing, the differences are shown much greater than they really are, so we can see them clearly. The Earth may be described as being very slightly pear-shaped, but the dips and bulges are so small that if you were far away in space, the Earth would look perfectly round. In recent years, scientists have found new ways to look at the Earth. Cameras placed in rockets have photographed the Earth from great heights. These pictures were taken from a rocket 700 miles above the Earth. They show clearly the curve of the Earth's surface. So, man has learned about the shape of the Earth in many ways. By watching moving ships, the Earth's shadow on the moon, rapidly turning objects, the orbits of satellites, and photographs like these. As we know now, the actual dips and bulges in the Earth are very, very slight. To scientists, however, even a difference of a few feet in many thousands of miles may be of great importance. For normal study, a perfectly round globe is still the best model we can conveniently make. If the Earth itself could be shrunk to the size of a school globe, it would appear rounder and smoother than any globe ever made.
In a quiet spot on the side of a hill, Jimmy and his family had a picnic one Sunday afternoon. There was soft grass and big trees. Not far away was a river. It was a good place for a picnic. Jimmy had brought a new book to read after lunch. The book was called Lands and Waters. What do you know about the lands on our world? What do you know about the waters? The book said, on our big round world, there are lands and there are waters. The book was about the different kinds of lands and waters that are on our earth. Jimmy's mother said he could see different kinds of lands and waters from the top of the hill. So wouldn't that be a good place to read the book? Father said he would go with Jimmy. Mother said she would stay with Jimmy's sister. So off Jimmy went with Father to learn about the surface of our earth from the top of the hill. Up and up they climbed. Higher and higher. Now they were high above Mother and sister. But they had to go higher. Finally, they reached the top of the hill. They could see for many miles around. Below them was the river. Beyond it were hills. Away in the distance were mountains. Although they could see many miles, they were seeing only a small part of the Earth's surface. If they were in an airplane or a rocket and could go very high above the Earth, they could see many more hills and mountains and rivers. And if they went high enough, they would see that the Earth is round and that there is more water on the surface of the Earth than land. They would see how big the Earth is and how much there is to find out about the lands and waters on the Earth. Jimmy wanted to begin. It said in the book, hills are one kind of land. There are many kinds of hills. From where he sat, Jimmy could see different kinds of hills. Some were not as high as the hill he was on. But some hills were very high. The hills had round tops and seemed to roll up and down, up and down. On the next page, the book said, hills are high, but mountains are higher. And that was right. The hills that Jimmy could see were high, but past the hills were mountains. Jimmy's father said these mountains were more than 10 times as high as the hills. Mountains are the highest kind of land. Sometimes they reach as high as the clouds. Because they are so high, it is cold near the tops of mountains. Often their tops are covered with snow, even in summer. The shapes of some mountains are different from the shapes of most hills. Most mountains are rough and steep. They are often rocky and not as smooth as most hills. Jimmy could see that the real mountains were like the picture of mountains in the book. On the next page, the book said, between mountains and hills, we find valleys. Jimmy knew this. He had just come from a valley. His mother and sister were down there now. That was a valley between hills. And Jimmy could see valleys between mountains. He saw one very big valley. A river ran through it, and many farms were there. The next page of the book said, Very wide and flat lands are plains. Jimmy could see land that was wide and flat, land that didn't roll up and down, that wasn't high and rocky. This was a plain. There was a river running across it. The plain had many farms. It was a rich plain. So Jimmy had seen some of the kinds of lands in our world. Hills and mountains, valleys and plains. But our world is made of more than just land. There is water, too, such as the river down there. Where did the water in the river come from, Jimmy wondered? And where was it going? Waters that flow are called streams. The picture showed a stream in a mountain. Jimmy's father said that some streams begin high in the mountains, where there is always snow. The water comes from melting snow and from rain. A stream that begins high in the mountains runs down the mountainside. Where the slope is steep, the stream runs rapidly. Sometimes it runs slowly, too. Down the mountainside it flows. Along the way, the stream meets other streams. They join into one and are bigger. Larger streams are called by a different name, rivers. Streams meet and form larger streams, which are called rivers. So the streams form a river, and the river continues flowing along. Along the way, the river meets other rivers, and they make a new, bigger river. Each new river is bigger than the ones that made it. Sometimes a river flows into a big, deep place surrounded by land. Jimmy's book said, when land is all around water, the water is called a lake. In some lakes, people have fun swimming or riding in small boats. People enjoy lakes and take care of them. Some lakes overflow, and the water runs on, making a river again. On and on the river flows. Now it flows through a valley. You often find rivers in valleys. Then Jimmy could see that the river flowed past the hill where he sat. But where was the river going? The book said, a river keeps running downward. Sometimes you can hardly tell that it is going downhill, but it always is. Along the way, people may be fishing. The river keeps growing bigger as it meets other streams and rivers and continues flowing along. Now the river is wide enough and deep enough for large ships to move upon it, carrying people and things from place to place. The river has come from little streams that joined into rivers, and small rivers that became the big river. And where is all the water going? It is flowing into a bay, which is part of a much bigger kind of water. Jimmy's book said, the biggest kinds of water are oceans. Oceans cover more than half of our world. And so the river finally flows into an ocean. As Jimmy could see from the map in his book, waters are all around the lands of our world. When Jimmy had finished his book, he had learned a great deal, and he wanted to find out many more interesting things about lands and waters of our earth.
Maps are everywhere. They're beside the pilot or navigator of every plane. They're in the glove compartment of almost every car. They're in every geography textbook. Maps are essential to the city planner, to the geologists hunting for oil, to every kind of military operation. The accuracy required of a map, of course, depends on its intended use. To the captain of this ship, it's critically important that the different depths of the water off this coastline are exactly what his charts say they are. It's critically important to the captain of this plane that the heights of the actual mountains are exactly as indicated on his charts. Not higher, not lower. Even in the construction of a building, it is important that it be located properly, not 10 feet to the west in violation of the building code or even on someone else's property. Accurate maps are important, but who actually makes them, and how are they made? Here's one man involved in one part of map making. Here's another. They both work for the United States Geological Survey and are quite literally measuring the surface of the Earth. Each new measurement they make begins at some point whose location has already been accurately established and marked on the Earth's surface with concrete and metal. The surveyor centers his instrument precisely over one of these known marks. From there, the distance to a proposed new point can be obtained. It can be measured physically with a special metal tape, or it can be measured electronically, a newer, faster, more accurate way to measure distances. This particular system, for example, directs a high-frequency radio signal to a reflecting unit. This instrument bounces the radio signal back to the transmitter. Extremely sensitive equipment in the transmitter measures the time it takes the radio signal to make this round trip. Suppose it takes 1/10,000th of a second to go and return. We know precisely how fast radio waves travel. We'll round it off to 186,000 miles per second for this example. Now the exact round-trip distance between the two devices can be calculated. 18 6/10 miles. 9 3/10 miles, just half of that, is the one-way distance. Now by changing instruments, we can use this measurement between points A and B to locate a third point, say point C. Standing at point A, the surveyor uses a theodolite, a sort of protractor with a telescope. He first measures the angle at A between his baseline and a line running to the new point at C. When his instrument is sighted precisely on the rod there, he knows angle A. The same thing is done from the other end of the baseline at point B. The surveyor accurately measures the angle there between the baseline and another line running to the new point at C. Again, he sights carefully on the rodman still at point C. Now, knowing the length of one side of a triangle and the two adjacent angles, the distances to point C can be precisely calculated. This method is called triangulation, and each side of the triangle formed by these 3 points can now be used as a base to locate still more points. Triangulation can be repeated until the area to be mapped is dotted with control points. That is, points whose horizontal location relative to one another are accurately known. In practice, of course, it isn't always simple to do this. In flat country, for example, where there are no natural high points or tall buildings, surveying teams must provide their own high points. Tall towers, like this one, are used as platforms by the surveyors. This allows them to sight over any obstructions, like trees, to the other points of the surveying triangle. The theodolite is hoisted to the top of the tower. From the tower, the job of triangulation is the same as it was on the ground. The surveyor carefully measures the needed angles. Here, because of the greater distance involved, sighting is done on a flashing light at the top of the other towers. The flashing light is easier to sight on than a rod. A still newer technique uses a helicopter instead of a tower. A weighted plumb line is dropped and suspended just above the new control point to be located. The helicopter is kept hovering precisely over this point, and the flashing beacon on top of it is in effect the top of a very tall rod. The direction and distance to this light is measured in the same way as if it were a rod, and its exact position is determined by triangulation. But more than horizontal points must be located to make an accurate map. The different heights of our Earth's surface must also be measured and recorded. And so a network of vertical check or control points is needed. These vertical control points are located in much the same way as the horizontal ones, beginning at sea level, zero elevation, the point where the land first rises from the sea. But sea level itself is constantly changing. It changes daily and weekly with the tides, even yearly as a result of gradual changes in the Earth's climate. So a standard sea level was created. Sea level readings taken at many stations over a period of time were used to calculate an average called mean sea level. This mean sea level became the standard, and from it, a network of vertical control points was established. From point to point, surveyors measured the profile of the land as it rises and falls. A newer, faster technique for measuring vertical distances uses this special vehicle. The fifth wheel in the center of the truck accurately measures the distance the vehicle travels. At the same time, a pendulum inside continuously measures changes in the slope of the road. These two measurements are fed to an onboard computer, which continuously converts this information into changes in height. As soon as the vehicle stops, the precise elevation of another vertical control point is known. The locations of these control points, both vertical and horizontal, are made permanent by the federal government with metal markers set in concrete. And it is around each of these control points that the mapmaker begins to collect the details of the terrain. Once, he actually had to go into the field and painstakingly measure and sketch every feature that was to be included on his final map. Today, planes collect in hours information that formerly took years to obtain. Within the plane, there is a high-resolution camera. It takes hundreds of extremely detailed, overlapping photographs of the Earth's surface, far below. The enormous amount of information stored on these hundreds of photographs is carefully extracted at one of the 4 regional offices of the United States Geological Survey. First, the individual photographs must be stereoscopically related to one another. The operator moves the tracing table of a special stereo device. He lines up the mark in the center of the table with 2 overlapping images of the same ground control point that appear in 2 adjoining photographs. The machine measures the exact location of this common point. When the operator presses a button, that location is recorded on a punch card. A computer then mathematically relates all the control points on the various photographs to one another. When this is done, The framework of these control points is transferred to the beginning map manuscript. With the photographs matched to one another, the detailed information that they contain can now be traced from them. One of the overlapping photos is projected onto the table with one color light, the matching photo with a different color. The special glasses that the operator wears let him see one photo with one eye, the other with the other eye. And instead of looking like two slightly mismatched images, they merge in his mind into a single three-dimensional image of the Earth as it looked beneath the airplane. Even the tiny dot in the center of the tracing table, represented here by a much larger black circle, seems suspended in space. He continually adjusts a knob beneath that table so that the dot of light appears to just touch the surface of whatever feature he's tracing. Steadily and precisely, the details of the Earth's surface on the photographs are transferred from them through the arms of a pantograph to the map paper. To show changes in height, the same instrument is used. The dot of light is locked at a specified level, and the operator traces all those points on the photographs that are that particular height. This produces a contour line. When one line is finished, the dot is set at a different elevation, and another contour line is added. When all the information this operator can get from the photographs has been mapped, field engineers must go back to pick up any missing information. Here, for example, the road being mapped was hidden from the aerial camera by trees. The field engineers also classify roads and buildings and add the man-given names of things that no camera can record. When all such information has been added to the map, the preparation of negatives for the printing plates begins. A draftsman scribes outlines around bodies of water. This negative will eventually be made into a printing plate that will reproduce these outlines in dark blue. A separate plate will be prepared to fill in the large water features with light blue. Another plate will show woods and orchards in green. These colors have become more or less standardized for maps. Still another plate will eventually reproduce roads and section lines in red. The plate containing the contour lines that describe the changing elevations of the land will be printed in brown. The plate that contains man-made features like buildings and railroads and names will be printed in black. When all the negatives for these government maps are completed, they go to Washington, D.C., where the plates are prepared and the maps printed. Certain maps are also prepared in shaded relief. An artist adds shadows and highlights to the sides of hills and mountains. This makes the relief features of an ordinary topographic map easier for the unskilled map reader to understand. Carrying this idea even further, some maps may be prepared in actual three-dimensional relief. To do this, a model is first made by routing out, layer by layer, exact duplicates of the contour lines. Using the contour levels as the basic relief, a realistic model of the Earth's surface is prepared. To make copies, the maps are printed on plastic. The plastic sheets are heated until soft, then drawn tightly against the model by a vacuum. But even while maps of the Earth's surface are being made, the Earth's surface itself is changing. The forces of nature and the forces of men combine to change the details of the surface. In addition, great parts of our Earth have not yet been accurately mapped. To do the job, newer, faster mapping techniques are needed, including astronomical theodolites used to sight on orbiting satellites. The work involved in accurately mapping the surface of our Earth is massive, and the job is a continuous one.
Because it's in a magnetic field, the Earth's magnetic field. This field exerts a force on magnetic materials, such as the steel the needle of the compass is made from. We can visualize a small magnetic field by sprinkling iron filings over a bar magnet covered with a sheet of plastic. The filings form a pattern. This pattern indicates the lines of force within the magnetic field between the north and south poles of the magnet. When magnetic fields interact, we see a different kind of pattern. This pattern occurs because like poles of a magnet repel, and unlike poles attract. A compass needle is a small bar magnet with a north and south pole. The south pole of the magnet attracts the north pole of the needle. But because the needle is on a pivot, it can turn. So the compass needle will turn along the lines of force as it's moved. At the other side, the south pole of the needle points to the north pole of the magnet. The lines of force connect the north and south poles, points of opposite polarity. The same is true of the magnetic field of the Earth. Here also, imaginary lines of force connect two opposite poles, the north magnetic pole and the south magnetic pole. But there is a difference between the positions of these magnetic poles and the geographic poles. Let's consider just the north geographic and magnetic poles and a location on the globe, here on the East Coast. A compass placed here does not point at the north geographic pole. It simply lines up with a line of force that connects the Earth's magnetic poles. On Earth, the north magnetic pole is defined as the pole towards which the north end of a compass needle points. Since unlike poles attract, it must really be a south pole, but we continue to call it the north magnetic pole to avoid confusion. If we extend a line in the direction the needle points, an angle is formed. Its measure is the angular difference between true north and the direction the compass points. This angle is called the angle of declination. Here it's 10 degrees west. In this particular location, the compass points 10 degrees west of the north geographic pole. If we change our location to here, the compass needle again lines up with a line of force, but at this point, the direction of the line of force happens to be the direction to the north geographic pole. So, there's no angle of declination, or declination is 0 degrees. On a map, we can mark points that have the same declination. They can be connected by a line called an isogonic line. This line connects points having 10 degrees west declination. Because of irregularities in the Earth's magnetic field, the isogonic lines themselves are somewhat irregular. These are some of the isogonic lines that connect points of equal declination in North America. This line connects points of 0 declination. It's called an agonic line. Maps showing lines of declination are called isogonic maps. Readings on the map show how many degrees a compass has to be corrected to point toward true north. The compass needle indicates a horizontal effect of the magnetic field, a declination. But the Earth's magnetic field also has a vertical component. Using a magnetic dipping needle, we can see that the magnetic field is three-dimensional. The dipping needle measures the angular difference between the Earth's horizontal surface and the direction of the Earth's magnetic field at that point. The angle formed is called the angle of inclination. Using a magnetized model of the Earth and a small dipping needle, we see that at this point in the northern hemisphere, the inclination is almost 90 degrees, locating the north magnetic pole. It's the same inclination that would result if the needle were above a bar magnet. The main magnetic field of the Earth is similar to the field of a bar magnet. Here is a simplified version of the lines of force of the Earth's magnetic field. A magnetic dipping needle near the north magnetic pole will come to rest almost perpendicular to the Earth's surface. Here, the inclination is almost 90 degrees. Near the equator, the needle is almost parallel to the Earth's surface. The inclination is about 0 degrees and helps locate the magnetic equator. We can connect points of equal inclination to form lines of equal inclination. 89 degrees, 88 degrees, and so on. The lines that connect the points are called isoclinic lines, and this is also how isoclinic maps are made. There is a third feature of the Earth's magnetic field. This is the strength or intensity of the field. Let's think about a magnet again. Most of the iron filings are attracted to the poles of the magnet, where the intensity of the magnetic field is the greatest. Intensity of the Earth's field is strongest at the Earth's magnetic poles, too. We can plot magnetic intensity of the Earth's field by connecting points of equal intensity. At points near the magnetic North Pole, the intensity is 0.60 Oersted. The Oersted is the unit of measurement of magnetic intensity. Intensity decreases towards the equator until it reaches a minimum of 0.25 Oersted, about 25 degrees south of the equator. The plotting of this kind of information is part of the work done at this magnetic observatory in Fredericksburg, Virginia. This is a proton vector magnetometer, a modern instrument used to measure magnetic intensity. At the control console, precise readings can be made of variations in the intensity of the Earth's magnetic field at this location. This is an observatory-type magnetometer used for measuring magnetic declination or deviation from true north. This instrument, an Earth inductor, measures magnetic inclination or dip. Measurements of the Earth's magnetic field are also made in many places away from permanent stations. On land, underwater, and in the air. The Earth's magnetic field is constantly being studied so that maps showing magnetic data can be brought up to date. In 1903, the North Magnetic Pole was here. Its position, here at present, indicates a westerly movement of 3 to 4 miles each year. We also know something else about the Earth's magnetic field. Many places on Earth once saw volcanic activity. Hot lava poured from these ancient volcanoes. As the lava cooled and hardened, tiny pieces of magnetic material in the lava lined themselves up with the magnetic field of the Earth that existed then. So, as the lava slowly changed into rock, a geologic record of the Earth's magnetic field at the time was permanently set or frozen. Geologists studying volcanic rock have discovered that the Earth's magnetic field has apparently disappeared and then reappeared with reversed polarity about 9 times in the past 3.5 million years. Scientists examining ancient rocks have also concluded that there's been a wandering of the magnetic poles. About 2 billion years ago, the North Magnetic Pole was located in North America, as it is today. Geologic evidence from rocks in North America indicates that it slowly moved across the North Pacific Ocean and eastern Asia to its present location near the geographic pole. What might have caused the shifting of the magnetic poles? One explanation is based on the belief that the Earth's magnetism may originate in the Earth's core of molten nickel iron. The rotation of the Earth may set up circling eddies in the liquid core that produce an electric current. This current generates north-south magnetic lines of force. The short-term variation of the poles may be due to changing patterns of motion in the core. The very long-term wandering of the poles can be explained by the theory of drifting continents. There are also external influences which can cause short-duration modifications of the Earth's magnetic field. One of the major influences is activity on the sun. For example, when there are solar flares, sudden temporary outbursts of electrically charged particles from the sun's surface, there are magnetic storms on Earth, temporary disturbances in the Earth's magnetic field. Radio communication is disrupted. Effects like these are being studied today with space probes and artificial satellites. These have been giving us a more complete picture of the Earth's magnetic field. Satellites and probes, equipped with magnetometers, have revealed that there are highly energized and potentially dangerous regions of charged particles surrounding the Earth. The particles are trapped in the Earth's magnetic field in donut-shaped regions of radiation. These are the Van Allen radiation belts, named for the man who designed the satellite equipment which resulted in their discovery. It's believed that the charged particles in the outer belt come from the sun's radiation, while those in the inner belt come mainly from excited atoms formed by the bombardment of the upper atmosphere by charged particles from the sun. The outer portions of the Earth's magnetic field are continuously buffeted by thin streams of electrically charged particles from the sun, traveling as fast as 2 million miles per hour. This solar wind, the source of the Van Allen belt particles, also modifies the shape of the Earth's magnetic field. Satellite measurements indicate that the Earth's magnetic field resembles a teardrop with a very long tail. Instead of being an orderly field extending almost endlessly into space, the magnetic field appears to be confined in a space called the magnetosphere. The magnetosphere is bounded by a thin layer of charged particles called the magnetopause. Toward the sun, the magnetosphere is only about 40,000 miles away from the Earth. On the opposite side, the solar wind draws out the magnetosphere like the tail of a comet, more than 3.5 million miles long. The width of the magnetopause varies from about 200 miles to 2,000 miles. Learning about the magnetosphere and the Earth's magnetic field is important to man's further exploration and understanding of space. Manned spacecraft that leave Earth for the moon or the planets must be shielded from the dangerous radiation in the Van Allen belts. A better understanding of these belts is necessary for the safety of space travelers. Further knowledge and understanding of the Earth's magnetic field will help illuminate the Earth's past and make safer man's way into the future.